Ooh, what happened? Hold on a second. Why are you not sharing? Nobody's seeing my screen, are they? Wow, it's not sharing. I don't know why. Gosh, what do I do about that? I'll try this one more time. Okay, that worked. I don't know what went wrong the first time. Okay, let me get the chat window open and then. All right, hey, welcome back. Sorry about the little delay in the beginning. I didn't even figure out what went wrong, but something went wrong, and now it's okay. So I've managed to come up with partners for most of the people who wanted partners. This was a very difficult one to try to pair compared to ones that I've done before, because for good reason, a lot of you maybe were less comfortable about choosing partners because that means using Zoom, and sometimes things can go wrong, as we've seen. So I understand, but with more people choosing solo, that gave me less freedom for pairing people in ways that made sense. I think this is going to be good. So these are the partners that I found and the people who are taking it solo. And I think most people got the day that they preferred. I think everybody got a day that could work. I think most people got paired who wanted to. And I think, if you see something glaring wrong here, like maybe I've put you someplace where, like, maybe I've put you on a Thursday, but you absolutely can't take the exam on the Thursday, let me know. Otherwise, these are the parents that come up with. Does anyone have any questions before we do other stuff?
They're both on 2 p.m., right?
I don't know, no, they're not both on 2 p.m. It's whatever the times are on the syllabus and also on the form that I sent out. One of them, I think, is at 11, one's at 2.
Where can we see the emails again of our partner?
Oh, I'm going to have to send it to you separately.
Oh.
So after this class, I'll send everybody I'll connect every pair by email.
Okay.
Okay. What else? So one nice thing about knowing all this information now is that you can get to know your partner. Maybe you can work together. Maybe you can practice talking through problems together and so on, and get some comfort level built up with each other, so that when it comes to the exam time, it feels more natural to work together on problems. And plus, it'll give you a friend to study with, and I think that's a nice thing for anybody to have. Okay, so give one more second in case there's more questions. All right, there's the exam. Let's talk about Stokes Theorem. So I just wrote Stokes Theorem down again. You have it in your notes. You can write it again if you want to. I just wanted to remind you, to use Stokes Theorem, there's these conditions. And two of them, well, one of them I had to sort of write in, the orange one, as it's obvious from the formula, but students miss it, so I'm going to count it as a requirement anyways. But what do you need? You need a three-dimensional vector field, and you need an oriented surface where the boundary has compatible orientation. And then also you need to check that you're actually doing the double integral of the curl of f and not just the double integral of f. So be careful, you can't use Stokes Theorem if it's just f ds. Okay, so that's what Stokes Theorem is, and we talked a little bit about meanings and so on for it last time. Let's try to do some problems involving it. So let's do some, maybe start out with some easier cases. So what if, let's think about case 1. Let's say the surface D has no boundary at all. What's an example of a surface that doesn't have a boundary?
R2.
R2, oh, okay, yeah, so absolutely, R2 is a surface that doesn't have a boundary, yes. That's not one that we would use though, because in order to integrate over R2, we're adding up something all over R2, and even though there are cases where you can integrate over an infinite space and still get a finite answer, remember doing improper integrals back in Calc 2? Usually integration over an infinite space is going to give you an infinite answer. So usually we're going to be thinking of spaces that aren't infinitely big, but still doesn't have a boundary. What's one that for which that's true? What about a sphere? So here, a sphere doesn't have a boundary. So, you can swim around, you can walk around on the surface of the earth all you want, but you're not going to find a hole in it. I mean, you might find a divot because there's some 3D-ness to it, but there's not a tear in it. There's not a hole. There's no boundary. Also, maybe like a cube or some other things, like maybe you've got a cone, but it has a lid on it or something like that. So there's plenty of surfaces that don't have any boundary. So let's think about if we're in that kind of situation. So let's see, cone with lid. What does Stokes' theorem say about that sort of situation? So if the surface doesn't have any boundary, then Stokes' theorem says that the double integral over the whole region is the single integral over the boundary. But there's no boundary. So what I mean by that is this set boundary of D is empty. So what does that integral have to be? I'm going to add up a value for every single element in an empty set. So how many things am I going to add up?
0.
0 things, that's right. And so then the value is going to be 0. Okay, so if the surface doesn't have any boundary, I don't care what the vector field is. Accumulating the amount of rotation all over that surface, there's going to be a net 0 amount of rotation. The positive rotation has to cancel with the negative rotation if it's a closed surface. Okay, so that's kind of a cool case. Here's another case. What about if F is conservative? That's one case. Here's another case, F is conservative. Then what?
There would be no curl.
We know curl, that's right, the curl would be 0. So then this left-hand integral is 0. True. What about the right-hand side? Why would that be 0? I mean, it's 0 already because of Stokes' theorem. We don't have to say anything else, but let's just think of this independently. Well, maybe I'll do one piece at a time. Okay, so then the left-hand side, curl of F is 0. So the double integral of curl of F dot ds has to be 0. We're going to add up 0 a bunch of times and make it 0. But also, right-hand side, the line integral around the boundary, oh, sorry, but not with the code. What's another reason why that line integral would be 0, besides that Stokes' theorem says that the left-hand side equals the right-hand side, so obviously it's 0. Can anyone think of another reason? Think about the equivalence theorem.
Because for every simple closed curve, it's equal to 0.
Yeah, exactly. Because anytime you integrate around a simple closed curve, if you have a conservative vector field, the integral is 0. How do I know boundary of D is a simple closed curve? Being the boundary of something means you have to close up. And simpleness also has to do with the surface doesn't intersect itself. So this equals 0 because boundary of D is a simple closed curve. And so by the equivalence theorem. And they're both equal to 0 because, you know, they equal each other because of Stokes theorem. So I'm just trying to get you to connect all of these pieces that we've thought of earlier to see that there's some consistency in what we've learned before to what we've learned now. All right, let's do a real example. Let's verify Stokes theorem. Oh, let me see if that's an example. If S is the surface, x squared plus y squared plus z squared is 16, and with z being equal to 0. And f is x squared plus y minus 4, 3xy, 2xz plus z squared. So remember, verify means we're going to do this computation, do both sides of the computation, and hope we get the same value. Okay, so let's do, you know, we have to do both of them. Let's do left-hand side first. So left-hand side is the double integral of the curl of f dot ds all over that surface called S. There's a lot of pieces in this part of the problem. What's one of the pieces?
ds.
You have to parameterize. And then what else?
Find the curl.
Find the curl of f. That's right. Okay, so there's a lot of different things. I guess it doesn't matter what you do. Let's parameterize first. Okay, it's another sphere. These things, it's horrifying, but it gets less horrifying each time we do it. So here's our sphere. Actually, it's not the entire sphere. It's just the hemisphere. Let me see if I can cut off this part. It's just the upper hemisphere. And so let's see, in the radius, it looks like it's 4. So it's going to be r of theta and phi is 4 sine phi cosine theta, 4 sine phi sine theta, 4 cosine phi. Since it's not the entire sphere, we only get, so theta is still between 0 and 2 pi. What about the bounds for phi? Hold on a second. What about the bounds for phi?
I actually had a question about this.
Sure.
Sometimes I saw that phi could be like from 0 to 2 pi in spherical sense, and I didn't really understand.
Phi should always be 0 to pi or less. Otherwise, you've got some ambiguity in how you describe your coordinates. So phi goes sort of from the top. Phi is 0, pi over 2. Phi is pi when you're pointing down. If you kept going, you'd get around to the back side of the sphere. But you can get there by going to the front side and doing theta rotating around to it. So we don't want to be able to get to a point using 2 different sets of parameters. So we have to limit phi to be 0 to pi. I guess it's possible if you wanted to get weird, you could have phi go from 0 to 2 pi and then limit theta 0 to pi. That will also work, but that's not as standard as the other way.
Thank you. And so in this case, we do 0 to pi over 2.
We're going to do 0 to pi over 2, exactly. Okay, so we parameterized it. Then what? What's the next thing?
Do we have to take the partials and then find the curl?
Yeah, that's right. We're gonna take the partials, have to find the curl at some point. So let's find r theta cross r phi. Okay, so r theta, we've done this so many times. It's going to be -4 sine phi sine theta, 4 sine phi cosine theta, 0. And then our phi is 4 cosine phi cosine theta, 4 cosine phi sine theta, and then negative 4 sine phi. So we took the partials, and then we have to take the cross product to get the normal vector. Okay, so I've got negative 4 sine phi sine theta, 4 sine phi cosine theta, 0. Then negative 4 sine phi sine theta, 4 sine phi cosine theta. And this last one is 4 cosine phi cosine theta, 4 sine phi sine theta, negative 4 sine phi. Okay, let's make that a little more reasonable. Okay, we're gonna do this cross product. So let's see the forward, oh, let me put some I's, some J's, and some K's in here. Okay, so the forward direction is going to be, I've got negative 4 squared, so negative 16 sine squared phi cosine theta. And then the backwards direction is 0. Then for J, the forward direction is 0, and the backwards direction is minus a minus. So a minus, so that's going to be minus 16 sine squared phi cosine theta, but sine theta.
I have a question.
Yeah.
For J, our phi, is that 4 sine phi sine theta or 4 cosine?
Oh, thank you. Yeah, you found a right here.
It's
Theta.
because
Yeah.
other ones is because, yeah.
Yeah, thanks. Let me make sure everybody can see what I changed. That should have been a theta instead of a phi. Thanks for fixing that for me. This is how, so you can see how it can help to have a partner. So Kelly was my partner now, and she was able to find when I thought theta and wrote phi down, and that could screw everything else up, right? So it's a good thing there's people watching me to make sure that I don't make it harder for myself later on. So
Could we also use a different way of finding the determinant? Because I know I'd use a different way. Or do you want to see?
well, okay, so I mentioned this early on. I use a different way to find a determinant as well. However, I don't use it in class because just about every single person who says they know a different way to find a determinant screws it up. They usually forget that they have to do negative of the J term. And since I saw like repeatedly that mistake happening, I thought, okay, I'm just gonna only show a way that I know that mistake doesn't happen. And then if you wanna do it a different way, then I hope you don't make a mistake. It's possible to not make a mistake, like I do it that way and not make a mistake, but usually in times of stress, students forget that. So that's why I do it this way. Yeah. Okay, so then I've got the K going forward is negative 16 sine squared phi. Is this right? What am I doing?
Isn't it sine squared theta?
Something's wrong here.
It was, I don't think it was your theta that was wrong. It was you have cosine phi, but then you made it sine phi when you moved it.
Oh, okay. Yes, right. So this whole thing's wrong, isn't it? That should have been 4 cosine phi sine theta. Both were wrong. I actually had phi written there, but you're right. This is sort of a bigger mistake. So this should have been 4 cosine phi sine theta. Okay, good. This makes more sense. So I'm going to have a 16 sine phi cosine squared theta minus 16.
Isn't it sine squared theta? I'm sorry. If I'm.
Oh my God, why can't I do this? Yes, it is. Don't be sorry at all. I'm sorry that I can't seem to get this right. Okay, hopefully that's okay. So when I say we've done this 100 times, apparently I need to do it 101 times so I don't make a mistake. Okay, so then what is this? This is negative 16 sine squared phi, negative 16, oh, cosine theta, negative 16 sine squared phi sine theta. And then remember this trick, we've done it a bunch of times before. If we factor out a negative 16 sine phi cosine phi out, then what's left over is a sine squared plus a cosine squared. So what's left over is 1. So I can just write that as negative 16 sine phi cosine phi. Okay. Haven't made any more mistakes. There's the cross product. What do I do with that?
Magnitude.
Well, magnitude, we use the magnitude when we want to do the line integral of a real valued function. But when we're doing a vector field, we don't use magnitude at all. We use the vector itself. So vector field, we're going to do vector dot vector. Real valued function, we do number times number. And so the number is the real valued function and the number is the magnitude. Here we've got a vector field, so we actually leave it as a vector for these cases. Then what should we do next, given that?
Is it the checking the orientation?
Yeah, we have to check the orientation. So let's, okay, well, let's see. How can we check the orientation? No orientation was even given. What does it mean to verify Stokes theorem? Well, no orientation was given. The implied thing up here was that you have to have compatible orientations. So even though nobody gave me an orientation, in order to do this problem, I have to decide that whatever orientation I choose on one half, I have to choose the compatible orientation on the other half. So let's just make a choice. Which orientation do you like for this hemisphere? Outward or inward? Upward or downward? I like upward. Let's do that one. So let's just write in here somewhere ahead of time. Let's say choose upward orientation. For S. There's no reason for that except that I had to pick. So I picked one. Okay, so if I choose the upward orientation, we've chosen upward orientation. What characterizes upward orientation? What part of our vector should we look at to see if it's upward?
Wouldn't Z have to be positive?
Z has to be positive, that's right. So so positive Z value everywhere. Okay, what does our parameterization have? Well, we're gonna have to be a little bit careful. Actually, so that's close when I say the word upward, and let's just realize that in fact, the upward orientation, if I take it all the way across, is gonna be totally horizontal when I'm down on the boundary. So it's actually gonna have a 0 Z value rather than, but in general, it's gonna be a positive Z value, so greater than or equal to 0. If I wanna check this, I should really just pick some values where I know what the parameters are. I could pick the North Pole if I wanted. It's a little weird because I don't really know what the theta parameter is. Theta equals anything works on the North Pole. Let's pick, I know what the parameters are here. So let's pick that point. So our parameterization at the point X is 4, Y is 0, Z is 0. The parameters are Ooh, that one I'm going to get a 0, and that's not really going to tell us that much. So maybe this isn't a good choice to pick. Does that make sense? Because I'm going to get a vector, and it'll have a 0 z coordinate, and I won't be able to tell which of these directions it is. So I have two choices. Either I could decide to call upward the same as outward, or I could choose a different place on there. Which one do you want to do?
If you call it outward, do you not have to check the point?
I'll have to check the point either way. No.
Oh.
Okay. I just might have to pick a different point if I don't call it outward.
If you call it outward, then it depends on something other than the z coordinate then?
Yes, that's right. If I call it outward, it depends on something other than the z coordinate. So there's pros and cons. I mean, there's challenges either direction to go. Well, we did one where we did outward and inward, not last class maybe, but 2 classes ago. So let's have this one be upward, just so we can see, so you have different things in your notes. So let's just continue with upward and realize that this point that I chose isn't going to be a good point to choose. Guess I can't just skip that. Let's choose instead, okay, let's choose the North Pole. It'll be a little bit weird. But let's see. So at the North Pole, so at the point 0, 0, 4, one choice of parameters are one choice is, let's see, phi has to be 0, but theta can be anything. So if I pick theta equals 0, that also works. So what is the parameterization? What is the normal vector at 0, 0? It's negative 16 sine squared 0 cosine 0, negative 16 sine squared 0 sine 0, negative 16 sine 0 cosine 0. Oh, this is 0. Okay, that's because it's at a weird point up there. I think really we don't really have a choice to do upwards for this one. I think we just have to do inward or outward. Sorry, I was hoping to show you a different thing to do, but maybe that doesn't make any sense. So let's choose upward equals outward. Okay, well, maybe this is a good lesson. Everybody, including me, including you, will try something and be like, oh, wait, I don't think that's going to be a good idea. And then you try something else and you try something else. That's just sort of the nature of math. And if you're genuine when you're doing mathematics, rather than sort of following a script, but I'm actually figuring this out with you, then you're going to see that we're going to try some things and be like, oh, wait, that doesn't come out how I thought, and try something else. So if you find yourself doing that, that's totally normal. So let's see. So rather than upward orientation, I'm going to say here outward orientation. And parallel to X, Y, Z. Yeah, okay, let's just leave that for a second, outward orientation. And then we don't care about this point. Let's go back to our original point. So at the point 4, 0, 0, the parameters are let's see. Theta is 0 and phi is pi over 2. And then we can plug those values in everywhere. Okay, so let's see. This is going to be sine of pi over 2 is 1. squared is 1 times cosine is 1. So it's going to be negative 16. That's going to be 0, and that's going to be 0. Okay. So does that point outward or inward? I'm starting at the point 4, 0, 0, and I'm going to add the vector 0, I'm sorry, negative 16, 0, 0. So that's going to go away like that. That's pointing inward. So orientation reversing. All right, what's next? Can we disintegrate? We got one more thing.
Find the curl of f.
Yeah, we got to take the curl of f, exactly. So curl of f. So let's see, what's f? We'll remind ourselves that f is xy, x squared plus yz, zx. And so the curl of f is the del operator crossed with f. So partial with respect to x, partial with respect to y, with respect to z, and then xy, x squared plus yz, zx. Okay, so the forward direction, partial with respect to y of zx, that's 0. Backward direction, partial with respect to z of x squared plus yz, that's just y. Forward direction for j is partial xy with respect to z, which is nothing, minus partial zx with respect to x, which is z. And then the last thing, forward is partial x squared plus yz with respect to x, that's 2x. Backwards is x. So I've got minus y minus z plus x. Did I do that right? Minus z. Yeah, okay, that seems right. Okay, so there's the curl. Now we can take the integral. So the double integral over the surface of curl f dot ds, double integral, curl f, everything has to be at the parameterization. So it's at r of theta and phi, dotted with r theta cross r phi, d theta d phi. Theta is 0 to 2 pi, phi is 0 to pi over 2. Okay, so that's going to be curl f at, well, we know what this is. It's 4 sine phi cosine theta, 4 sine phi sine theta, 4 cosine phi. That's just the parameterization. I remember that because those are just spherical coordinates. Then I'm going to dot that with r theta cross r phi. So what's that? R theta cross r phi is right here. So I've got negative 16 sine squared phi cosine theta. Negative 16 sine squared phi sine theta. And negative 16 sine phi cosine phi. D theta d phi. What's next? What do you do next? Can I just do that dot product?
You have to plug the values of R into curl.
Yeah, good. I have to plug the values of R into curl. So if I look up here to see what the definition of curl is, curl of F is at negative Y, negative Z, X. Okay, so if I evaluate there, negative Y is going to be negative 4 sine phi sine theta. Negative, is it negative Y, negative Z? Yeah, negative Z is going to be negative 4 cosine phi. X is going to be 4 sine phi cosine theta. Then I'm going to dot it with this thing. Okay, and do the dot product. Let's see what we get. So first times first, it's going to be negative. It's going to be 64 sine cubed phi sine theta cosine theta. Okay, so that's doing this term times this term. Now I've got plus 64 sine squared phi cosine phi sine theta. Okay, that's this one times this one. Then I'm going to have, looks like a minus. Wait, is this one supposed to be minus as well? Nope. Then minus 16 sine squared phi cosine theta. D theta d phi. What is
Professor,
64?
I'm sorry.
Yeah.
I missed where you plugged in the curl of F. Could you show where you did that again, please?
Yes. So here's the curl of F. So that's negative Y, negative Z, positive X. Let me make sure. Did everybody check that I did that one right? See, that's going to be 2X minus X. So yeah, okay, so I think I did that one right. Okay, so negative Y, that's going to be, here's the Y value. So this is negative Y. Here's the Z value. So this is negative Z. This is positive X.
And then wasn't the Z value cosine phi sine phi as well? It wasn't just cosine phi?
This is the Z value of the parameterization and not of the tangent. Yeah, okay. Did anyone catch any of the mistakes? Oh, I guess that one wasn't a mistake, but there's been mistakes earlier. Okay, so is there anything that we combine here? There's a sine squared, but I don't think that helps with those two. Yeah, I'm not sure that that really helps with those two. So let's just do the antiderivative. So first we have to do with respect to theta. So let's just look at what the theta terms are. Here's one of the theta terms. Here's a theta term. Here's a theta term. All of those we can handle. This one we're going to treat as a u sub. Like, for example, if u is sine phi, sine theta, that's going to be how we're going to do that one. So it's going to be this 64 sine cubed phi is just a constant. And then what's the antiderivative of u times du? It's going to be 1/2 u squared. So sine squared phi, 1/2 of sine squared phi, theta, sorry. Okay, so that's that one. Plus, well, whose derivative is sine? It's cosine. Negative cosine. So negative 64 sine squared phi cosine theta. And then whose derivative is cosine theta? It's sine. So this is going to be negative 64 sine squared phi cosine phi sine theta. And all that's between 0 and 2 pi. Okay, so let's plug in 2 pi everywhere. It's going to be 64 sine cubed phi. Well, let's just deal with the 1/2. So let's say that's 32 sine cubed phi times sine squared of 2 pi minus 64 sine squared phi cosine phi times cosine of 2 pi minus 64 sine squared phi cosine phi sine of 2 pi. All of that minus the same thing at 0. d phi. Okay, not everything's 0. Some things are 0. So let's see, sine of 2 pi, that's 0. Sine of 2 pi, that's 0. Sine of 0 is 0. Sine of 0 is 0. But I've got two terms that aren't 0. So that's going to be, well, I won't skip any steps. So it's going to be negative 64 sine squared phi cosine phi times 1 minus, oh my gosh, look how many minuses are. Minus here, and minus here, but then this is also a minus 1. So that's going to be minus 64 sine squared phi cosine phi. And those combine. So negative 128. And this is set up nicely as a U substitution. So sine cubed comes from sine to the third power. So 1/3 sine cubed phi to the 2 pi. Oh my gosh. Ha! Is this going to be 0? Oops, that's not 2 pi, that's pi over 2. That's why. Yay, okay. Okay, so sine cubed of pi over 2 minus sine cubed of 0. Negative 128 over 3. I sure hope that's right, because imagine if we have to try to trace through all these steps to see where I've made a little error. We've already caught some errors, which I'm really grateful for, but maybe there's another one.
Can you repeat one more time why it was negative 64, like why the second one was negative?
Yes, okay, so this minus,
There's something.
so let's see, this minus right here, well, maybe that's not visible. This minus right here is because of this minus. And then this minus right here is because you plug in at the top bound minus plug in at the bottom bound. And then this -1 is because cosine, because cosine of 0 is +1, so that should be a plus.
Should be 0 then?
Oh, okay, this makes me really nervous. Uh-oh. Does anybody see any other mistakes as we were going through? Why are you doing that stuff? Well, let's see. Maybe it's not a mistake. How can we find out?
Didn't we also lose the negative sign from it being orientation reserving? Or did we even have one?
No, we should have put that. Okay. Gosh, today's been a horrible day. So I'm glad you're here to correct things. Yes, there should be a negative sign. And then we get 0. How can we check whether we made a mistake besides looking through everything?
Do it the other way.
Yeah, let's do the other side of Stokes Theorem. Keep our fingers crossed. Hope this is right. Otherwise, I probably won't be the only one to cry. Okay, so let's try the other way. So the right-hand side of Stokes is the line integral f dot dr along the boundary. Well, it has to be compatible orientation. So let's think about what the orientation has to be. So let me draw it again. So the orientation that we chose for the surface is like this. Outward or upward. And so the corresponding one, the compatible one for the boundary, that's the direction, so that if we walk around in that direction, with our heads up in the direction of the green arrow, the surface is on our left, and that's going this way. Okay, so let's parameterize the curve. Okay, this is a circle of radius 4. So remember, r of t is 4 cosine t, 4 sine t, and z value is always 0 because we're in the xy plane. And t goes from 0 to 2 pi. Let's check the orientation. Well, let's see. Our parameterization goes counterclockwise viewed from above. What about the desired one? Compatible orientation is which way? Is that counterclockwise or clockwise?
Counterclockwise.
Also counterclockwise, yeah, good. So this one is orientation preserving. Then there's a line integral. Okay, so let's see. The integral around the boundary of f dot dr, everything has to be at the parameterization. So it's going to be t values, 0 to 2 pi, f of r of t, dotted with r prime of t dt.
Can you explain how you found out it was orientation preserving again?
Okay, so if I think about, so our parameterization, we're probably comfortable understanding what's going on here. As t increases, we go this direction. So at least our parameterization has us go counterclockwise when viewed from above.
Yeah, I was confused about the next part.
Yeah, okay, so I'm just saying all of them together in case somebody else was confused about that part. What is the desired one? Well, we had to decide what was compatible. So maybe for the outward normal that we chose a super long time ago, all the way up here when we chose an orientation for our surface, we happen to choose the outward one. Well, what's compatible with that way down here? What's compatible with the outward? Well, if our head is, oh, it takes so long to scroll. If our head is pointing, if upward counts as the direction of the green arrow, then as we're walking along the curve in the direction of the yellow, the regions, of the direction of the pink, the regions to our left. So the correct orientation, the compatible orientation for the green, this is the compatible orientation on the boundary of the surface. And then that one also, if I look from above, that one's also counterclockwise from above. All right, so f of r of t, what's f? Well, let's see, f is x, oh, let's put r of t in first. So it's gonna be f of 4 cosine t, 4 sine t, and then 0, dotted with r prime of t, it's gonna be negative 4 sine t, 4 cosine t, 0 dt. And let's just try to recall, so I don't have to keep scrolling back. F looked like xy, x squared plus yz, zx. Okay, so x times y, that's going to be 4 cosine t, some 4 sine t, that's 16 cosine t sine t. And then x squared is going to be 16 cosine squared t, plus yz is going to be plus 0. Zx is also going to be 0. That product is negative 16 cosine t sine squared t. And then plus 64, wait, that should have been 64. Plus 64 cosine cubed t. Okay. Anyone have questions about this one so far? Hey, if I factor out a 64, oh, it's a plus and a minus. I hope I made a, did I make a sign error? I wish I made a sign error. That'd make things so much nicer. No, I don't see a sign error. Darn. Okay. Well, whatever. This is going to be just a little bit longer to integrate. What do we do with this? We take save a cosine t, and then write the cosine squared as 1 minus sine squared t. That's kind of nice still, anyways. So I've got negative 64 cosine t sine squared t plus 64 cosine t minus 64 cosine t sine squared t. Yay, and those things cancel. Oh, they combine. I just keep wanting to cancel things. So I guess I've got negative 128 cosine t sine squared t plus 64 cosine t. And then we can anti-differentiate. So this thing, if I did a u sub where u was sine of t, then this thing counts as the du. So that's going to be negative 128 over 3 sine cubed t. And this is going to be plus 64 sine t. And that's 0. So we got 0 on both sides. This is going to be negative 128 over, well, you know, sine of 2 pi is 0, sine of 0 is 0, everybody's 0. we got the same answer. So if we made any mistakes, we made the same amount of mistakes on both of them. Same answer no matter which way that we calculated. So this verifies Stokes' theorem for this example. Which way is easier? The line integral side or the surface integral side? Let's go back and look at Stokes' theorem. Which side is
The
easier?
right side.
The right-hand side, the line integral side, is a lot easier. Usually that's going to be the case. So this side's usually going to be easier. It could turn out that this line integral, the vector field's so complicated, but when you take the curl, it goes away to almost nothing, in which case the left-hand side's easier, but in general, the right-hand side is usually easier. Okay, so there's our example for Stokes' theorem. We'll probably do another example. These are pretty long. So let's just take a moment to see if there's anybody wants to ask a question, anyone just want to take a breath, anything like that. Look at anything again?
I have a quick question,
Sure.
or kind of like a question. I just have a really hard time, like, understanding how the orientation affects, like, how you do the problem and like how that check works. On the homework due today, for example, I had a really hard time trying to figure out what I would set up different based off of the orientation differences for each question.
So what you set up different is what I missed, but that Delaney called me on, which is, so here, when I was orientation reversing, what's a good color I use? Here, when I was orientation reversing, what that means is I could set up my integral just as I thought, but I had to add a negative sign in the front because my parameterization gave the wrong orientation. So once you know if your parameterization is orientation preserving or reversing, then you can account for that by putting a negative sign in if it was reversing, or leaving it alone if it's preserving. Did that answer your question, or did you have a different question?
I think that answers it pretty well. The only other question too I had was if could you scroll up please a little bit,
Yeah.
to where you find R of the cross product.
Mm-hmm.
Does it? I kind of run into an issue where I accidentally did one the wrong way. I did it R phi crossed with R theta.
It's not
And
a
it's
problem.
still, yeah, it's not a problem. All
No.
right, that's I
Here's
know
what
that they're different answers, but
well,
it
you
gave
should.
the right
You shouldn't. You shouldn't get your different answers. Here's why. Because if I did, so what's a color I haven't? Gosh, I use all these colors so much. How about lime green? Okay, so if you had done R phi cross R theta instead, what that means is, remember, if I do A cross B, I get a vector going this way. If I do B cross A, I get the same vector but in the opposite direction. So what you should have gotten was the negative of that vector. And so then what you should have gotten was orientation preserving. And so then you wouldn't have added a negative sign here, but the negative sign would have been built, so there would have been no negative here if you'd used R phi cross R theta, but there would have been a negative sign here. R phi cross R theta. So in the end, you get the exact same answer.
Okay, yeah, that makes sense. Thanks.
It's a good question. What else? All right, let's see. So I did that. Oh boy. I think something went wrong here. I used the wrong vector field. I'm so glad it worked. Down here, is that the vector field I started out with? Oh boy, okay. So when I looked at my notes, I did the wrong thing. So I put this vector field is the correct one, but I didn't use that one. I used this vector field, which was from the next problem. But since I used, see, it takes so long to scroll. Since I used the wrong vector field on both sides, it still worked. But I didn't mean to do it that way. So let me just correct it up here. This has been like an incredibly bad day for typo mistakes. And I'm sure this is a frustrating day for it to happen with the content being so hard. I really apologize for that. I don't know what's happened to me. So let's just change the problem to be the same thing that we used, which was xy, x squared plus yz, zx. Okay, so that's what it means to do a Stokes theorem problem. Well, that's verifying it. If I wanted to do a Stokes theorem problem, I'm kind of afraid to use a made up vector field. Yeah, let's just use the same vector field, because if I make up my own vector field, the chances that it will integrate easily enough is pretty slim. Do you know what I'm saying? So it's good to use the problem. We got lucky that when I picked the wrong vector field, it also happened to work. Let's think of another example. Do you want to see another example, or did I? Is everybody frustrated enough with computation that we need a break? Who would like to try another example? Nobody. Do you want to try one yourself?
Can we go over another example?
Yeah, let's try another example. I'd have to look it up to use a different vector field, but yeah, I'd have to look one up. Let me look one up to get a different vector field. Hold on, let me get it. Oh, I know, I can just look one up out of our fun pack. Let me do that. Do you remember, does everybody remember that there's a fun pack? For these, I'll show it to you. Okay, there's surface integral practice. Here it is. Did it share? Can you see it? Oh, I see it, okay. Okay, so here's a bunch of surface integral practice problems. I recommend that you do them. There's 17 of them. They're long. All these problems are long, but this is a chance to do a lot of practice. So let me think of one that would be Stokes theorem. Okay, let's do number 6. Number 6 is Stokes theorem. So number 6 on the fun pack. Number 6 says, calculate the flux of the curl of f of x, y, z equals 3y 5 minus 2x z squared minus 2 over top half of the sphere radius 3, square root of 3. With upward orientation. Oh, it's the same shape. Yeah, there it is. Okay, so here's a sphere of radius square root of 3, top half, same picture. So the radius is square root of 3. And it has upward orientation, so upward's the same as.
Professor, I think you have to switch your share screen.
Oh, thank you. Okay, so what's upward orientation? Okay, so I'm being asked to calculate the flux of the curl of F. So there's a curl in there. And also I have a surface and that has a boundary. So what are the conditions for Stokes theorem? So what are the three things? Can anybody remember any of the conditions? Yeah, go back and look if you don't remember.
Three D vector.
3D vector field, absolutely, that's one of them. What else?
Compatible orientation.
Compatible orientations, yep. And then also we're asked to integrate the curl of F and not just F, and we are here as well. Okay, so we have this. So let's check the. So we want to use Stokes theorem. So this is how I write this up. Want to use Stokes theorem.
Wait, what's the vector field?
It's right here.
Is it just,
Oh, there should be a comma somewhere.
yeah, I
Let me
think,
see what I missed. 3y comma 5. Yeah, this should be a comma. 5 minus 2x. Okay. Okay. So want to use Stokes theorem. Let's just check. First of all, F is a 3D vector field, so that's good. We need compatible orientations. So let's see, if I have an upward orientation on the surface, is compatible with the counterclockwise as viewed from above orientation on the boundary. And the last thing is we were asked to integrate the curl. Okay, so I've checked all the conditions. So I'm allowed to use Stokes theorem. So in order to use Stokes theorem, I can replace a surface integral with a line integral around the boundary. So if you want to write down, so recall Stokes says that the double integral of curl f ds is equal to the single integral of f dr around the boundary. So if I want to do that single integral, I need to parameterize the boundary curve. And since the radius is square root of 3, it's going to be r of t is square root of 3 cosine t square root of 3 sine t and 0. This one's very similar to the last one. I'm sorry I randomly picked one that was similar enough, but they won't all be similar. And then 0 less than equal to t less than equal to 2 pi. Check the orientation. The desired orientation is counterclockwise from above, and so is our parameterization. So it's orientation preserving. So now we can do the problem.
Professor, just quick question one more time.
Mm-hmm.
So rather than actually calculating the flux itself, we use Stokes theorem to simplify the actual integral, which means we have to reparameterize everything and then resolve the problem.
Well, we're not going to reparameterize everything because we didn't parameterize the surface itself. We're just going to parameterize a different thing.
Gotcha.
Yeah. The reason we did both in the last problem was because it was verify, so we wanted to check both. We had to do both calculations. But in general, if we're asked to do one calculation, we could say, no thanks, I'm going to replace it with one that's easier.
Thank you.
So evaluating the integral, we were asked to integrate the curl of f dot ds over the surface. And we're going to replace that with the line integral around the boundary. So notice here's where we started with what we were asked. And then here, this is because of Stokes theorem. Okay, so this is going to be 0 to 2 pi f of r of t dotted with r prime of t dt. F of square root of 3 cosine t square root of 3 sine t 0 dotted with negative square root of 3 sine t square root of 3 cosine t 0. Now we plug it into the vector field. So the vector field is, so I'll write it off to the side, even though you wouldn't put that in here. But I've got a small screen, so I have to. So the vector field is 3y 5 minus 2x z squared minus 2. So 3y is 3 square root of 3 sine t. 5 minus 2x, 5 minus 2 square root of 3 cosine t. Z squared minus 2. Oh, no. Okay, so I just plugged it into the vector field. Doing the dot product, I'm going to have negative 9 sine squared t. Then it's going to get 5 root 3 cosine t minus 6 cosine squared t dt. I'd probably be tempted here to do something like, it's not required, but I probably want to do something like, this is negative 3 sine squared t plus 5 root 3 cosine t minus another 6 sine squared t minus 6 cosine squared t, so that I can take advantage of this sine squared plus cosine squared t. Does that make sense? I've taken the 9 and split it up into these two parts. So 5 root 3 cosine t minus 3 sine squared t minus 6. And then that's going to integrate to be 12 pi or something like that, negative 12 pi. So if you want to do it if I just remind you, I have to change this to minus 3 halves 1. Oh, there's going to be another piece of it. 1 minus cosine 2t. Okay, these pieces we can anti-differentiate now. I guess I can put the -3/2 minus, that's going to be minus 15/2. That's minus 15/2 t. And then the cosine came from a sine. And then the cosine 2t, that came from a 1/2 sine 2t. Everything goes to 0. The sine at 2 pi is 0, and the sine at 0 is 0. So it's just going to be -15/2 times 2 pi minus 15/2. That's 0. The thing I care most about for this problem, and the thing that's going to be the most points whenever I grade, is not all the details of the integral, because sometimes we're going to make mistakes, and then we can make a problem that's hard to integrate or whatever. But the things that I really care about is, well, and in fact, you can see this if you look at my grading of the last exam. The things that I care about are things like, did you recognize that Stokes Theorem was going to be a good choice to use here? Did you know that was the name? Did you know what the conditions were? And did you check that you had the conditions? Did you set this integral up correctly? Did you show me where you used Stokes Theorem? So all the way up to here, that stuff's critical. From here to here, I'm like this, I think in the last exam, all that was like a point. Can you integrate, can you not integrate? Maybe you made some mistakes, some algebra mistakes, you can lose a point. But the bulk of it, the thing that I care about is the Calc 3 stuff. And the Calc 3 stuff is from here on up. Okay, so what we need is to do, 20 more problems. It's sad, but it's true. Luckily, you've got 17 more problems just waiting for you right here on the Sunpack, or 16 more since we've done one. And then there's some homework as well. So do the homework for 13.8. Obviously, the homework for 13.9 will be due. 13.9 isn't very long. We can finish 13.9 in like half the class or a little bit less. So for the last class, we'll do 13.9. See if there's any sort of general questions, and then I'll give you some time to do an evaluation. And then we'll have some time, maybe next Thursday, which is not a class period, but maybe I'll just, during class time, I'll just be here. And if you want to work on the fun pack problems, I can be here to kind of help you if you get stuck. Does that time work for people?
Mm-hmm.
Would anybody actually show up for that?
I would.
Probably would. Yeah, I would.
Okay, so let's plan for that. So try these problems. They're gonna be long for sure, and it's gonna be difficult at first for sure, and you're gonna get better and better at them. So just try a lot of problems over the weekend. Generally, a lot of questions, and I can come early if somebody contacts me. I can come early for office hours on Tuesday as well. So so I'll be here. Okay, have a great weekend. Good to see you. One more class left. We almost survived it. See you later.